Welcome to the 22nd lecture on digital simulation. In this video, we will discuss artificial damping in numerical techniques. So we will illustrate artificial damping with the help of a simple circuit, a simple example. This is also known as numerical damping. So consider an LC tank circuit shown here. There is an inductance, a pure inductance L, and an ideal capacitor C. The current through the inductance is denoted as IL and the voltage across the capacitance is denoted as VC. So the differential equations governing the system are C into dVC by dt equal to minus IL. So C into dVC by dt is the current through the capacitance, that is equal and opposite to IL. So there is a minus sign here. And voltage across the inductance is nothing but L into dIL by dt, and that is same as VC, capacitance voltage. So dVC by dt equal to minus IL by C. That is equation number 1. dIL by dt is equal to Vc by L. That is equation number 2. So if you solve these two differential equations analytically, dVc by dt equal to minus IL by C and dIL by dt equal to Vc by L. If the equations are solved analytically, then we will get Vc of t equal to cos omega t and IL of t is equal to sin omega t. In this case, for L is equal to 1 Henry and C equal to 1 Farad. These are the values we are using. Okay, this is the analytical solution. So the capacitance voltage, if you plot the capacitance voltage, then it will be a cosine wave of constant amplitude equal to 1. But if you simulate the same using backward Euler method, you can see that the result shows a decreasing amplitude. If you solve the system using backward Euler method, you will get decreasing amplitude. Amplitude is decreasing. So that phenomenon is known as artificial damping. Whereas if you simulate this using trapezoidal method, then there is no issue. Amplitude remains constant at 1. Amplitude of the capacitance voltage is constant. So there is no artificial damping in trapezoidal method. So let us see what is the reason. Trapezoidal method is so suitable for circuits with no dissipation, purely oscillatory circuits, because in LC tank circuit there is no dissipative element, there is no resistance. This is an ideal inductor and an ideal capacitor. So this is a purely oscillatory system. So in such systems, if you use backward Euler method for simulating the system, you will see damped oscillations. There will be diminishing amplitude. Whereas in trapezoidal method, there is no such problem. So trapezoidal method will be preferred over backward Euler method in such systems. So let us analyze this. So the first differential equation is dVc by dt, that is Vc dash is equal to minus IL by C, and dIL by dt, that is IL dash is equal to Vc by L. So these two differential equations can be written using the dummy variables y1 and y2. y1 dash is equal to minus omega y2 and y2 dash equal to omega y1, where y1 is this quantity, root of c by 2 into Vc, and y2 is root of L by 2 into IL. If you use these substitutions in this differential equation, these equations will get converted into this form. y1 dash is equal to minus omega y2, y2 dash is equal to omega y1. Now this differential equation can be solved using backward Euler technique. So y1 n plus 1 will be the previous value y1 n plus h into this quantity evaluated at n plus 1th instant, minus omega yn plus y2 of n plus 1. Similarly, y2 n plus 1 will be y2 n plus h into the right hand side, omega y1 evaluated at n plus 1. So this can be written in matrix form like this. And y1 n plus 1 and y2 n plus 1 we can solve for these two. So y1 n plus 1, we will get an expression for y1 n plus 1 and expression for y2 n plus 1 from this matrix. You can just invert the previous matrix and it will take this form. And y1 n plus 1 will be this, and y2 n plus 1 have this value. And the total energy in the circuit is half into C of Vc n plus 1 square plus half into L into IL n plus 1 square. Energy stored in capacitance is half CV square. Energy stored in inductor is half Li square. And we are calculating the energy at n plus 1 instant. So half C Vc n plus 1 square is nothing but y1 n plus 1 square because of this substitution. Half C Vc square is y1 square. Similarly, half L IL square is y2 n plus 1 square. And if you do the substitution, you can see that y1 n plus 1 square plus y2 n plus 1 square is not equal to y1 n plus 1 square plus y2 n plus 1 square is not equal to y1 n square plus y2 n square, because here you can see there is a denominator greater than 1. So y1 n plus y1 n the whole square plus y2 n the whole square is less than this left hand side. So the energy at the n plus 1th instant is now less compared to the energy at the nth instant. So the total energy keeps on decreasing, which is manifested as decrease in the amplitude. So there is actually no physical change in the energy, but in the numerical simulation, we are experiencing a diminishing amplitude. That is why when you simulate this system using backward Euler method, you see a decreasing amplitude. Amplitude is decreasing. Whereas if you do the analysis for trapezoidal technique, in trapezoidal technique, you will not see any diminishing amplitude. But trapezoidal technique has another drawback. Even though the amplitude has zero error, but there will be an error in the phase. If you compare the exact solution and the trapezoidal solution, you can see that there is a phase shift. If you observe closely, you can see there is a phase shift between the exact solution and trapezoidal solution. That is one drawback of trapezoidal method. So this is about artificial damping in numerical methods. Thank you.